All right, maybe we can start. Welcome to the afternoon session. And it seems like this session has everything: simulation of open systems, thermal states, ground states, simulation of materials. And we are going to begin with thermal state algorithms for thermal states, and Anthony is going to tell us about that.
Thanks for the nice introduction. While you guys are still walking in, let me just ask, so who have heard what a Lindbladian is? Who know? Oh, that's great. Okay. So yeah, so this talk is going to be a mix of many talks I'm very lucky to be involved with. So these are all nice co-authors. It's going to be covering a few topics along the line of thermal state preparation and so some hope for quantum advantage. Okay. So it's going to be like a summary talk. And just by the way, if you have been in Andra's talk, this is going to hopefully complement what he speaks about. So I'll actually skip most of the things he mentioned and sort of go for more of a physics-inspired angle. Okay. Okay. So here's our goal. We all love Gibbs states. This is a state that's defined based on the Hamiltonian and a temperature. Right, and I just set this to be our goal. We want to prepare this state on a quantum computer. Okay. And you may ask, if I have this state, what can I do? At least for me, if I really have a quantum computer that prepares a Gibbs state, I would do these experiments to learn about phase transitions and their sort of thermal properties and transport properties. For example, I can try to test if my material is a superconductor or not. Right, but at the same time, I also want to mention there's sort of a different interest, just coming from this quantum computing community, is the search of quantum advantage in quantum simulation. Okay. So so while factoring, this is a very famous example that people sort of know and love. Quantum simulation, even though people kind of widely believe, or maybe let me just ask: so who believes quantum simulation will have practical quantum advantage? Okay, so there's also a majority here, it seems. However, at least to me, it seems very hard to find like a very concrete, definite argument for such a speed up, even though we kind of believe it. And we have been working so hard. In this morning, we have seen so much algorithmic work trying to just improve, the performance of Hamiltonian simulation. But despite all these works, it's still very hard to pin down like a very concrete instance where there's definitely a quantum speedup. And so the challenge is that there's very good classical algorithms. We don't actually have a big working quantum computer. There are also many problems you can define in quantum simulation. So it's kind of messy. But hopefully today I will try to convince you and just give you some partial evidence that cooling or this thermalization, so these some kind of emerging field could be such a problem. Okay, and then so the associated algorithm is precisely the one Andras mentioned this morning. In a computer science language, these are called quantum Gibbs sampling algorithms or quantum Gibbs samplers. Okay. And I also try to cover very quickly two arguments for quantum advantage. It's very hard to have a sort of fully convincing argument. So these two are also just kind of partial, and they're sort of limited by their own, each in their own ways. So the first argument for quantum advantage is that at very low temperatures, if you simulate these algorithms, they're as powerful as a universal quantum computer. So this is like implicit evidence for quantum advantage, right? Because factoring is hard, you don't expect low temperature physics to be classically easy. And then I'll also cover a result that's very recent that discuss constant temperature Gibbs states. Okay, so there, the hardness is weaker, but then the temperature is higher. Right, so there the hardness is sort of borrowing from the hardness of some random circuit sampling instances. Okay, but before we talk about these so cool, arguments for quantum advantage, I would like to start just with defining, okay, what is cooling? What is this Lindbladian thing? And can we actually define them and sort of have algorithms to simulate them? Okay. Right. Okay. So let me start with the sort of a starting point of behind this whole proposal. So since we're all trying to find quantum advantage, but now the largest working quantum computer is still pretty small. But actually, there is one actually a working example of a quantum computation in some sense, and that's your refrigerator. If you ask your experimental colleagues or yourself as experimentalists, whenever you want to find some quantum physics, you just cool it down, and it just seems to work. Right. So to me, this seems like some crazy magic must happen. This is nothing that like any quantum algorithm we have seen. This is a very simple principle, and almost always works. It's super resilient. It just kind of works. Right. Well, usually when you design quantum algorithm, you might think it's very prone to error. You have to tune things very carefully. It seems to be opposite. Right. So as a starting point of this program of thermalization and quantum algorithm is to hope that we can exploit this cool sort of seemingly very amazing power from cooling. Okay. So, but to do that, to make sort of precise progress, we have to first write down something that describes your refrigerator. Okay. And once you have a precise model, once you have a definite embodience, you can try to simulate it and try to understand its gate complexity and so on. Okay. Right. So we're going to take this route, trying to understand how what magical things a low temperature heat bath can do to your favorite quantum system. And at the same time, this morning with Andras, he has actually talked about a completely different angle. This is actually eventually leads to almost the same thing. So it's kind of amazing that you can start from either the physical region or sort of the algorithmic design, and these two things actually meet in the middle, and they come together in some kind of quantum version of global dynamics that Andras has mentioned already. Okay, but I will not talk about these things on the right-hand side. Okay, so just more focus on just this physical pursuit of trying to model what happens in the open system in a thermal environment. Okay. Okay. So this first part of the talk is just to give a quick views on what we know about the thermal embodience. Some of them are very, very old literatures, but I'll also try to smuggle in some of the recent algorithmic developments. Okay, so just very quickly review. I know you all love embodience. So this is a generic form of a master equation or Lembodian that governs a continuous time Markov process. So this has already appeared today. Okay, and of course the point is that you have to choose these L accordingly, these Limdot operators, in order to describe correctly the system you care about. Right, so if you're in a thermodynamic Lembodians, these L's, these Limdot operators take particular forms. They're not just any Limdot; they have some very particular form. So let's consider a physical model. Okay, so this is the really physical model. Whenever I say thermalization, I mean this model. So take your favorite system and then put it in thermal contact, in a weak contact, to a Markovian thermal bath. And further, you want the bath to be really, really big, and your system to be very small. And also the coupling has to be very weak. And this sounds a little restrictive, but this is also the regime where more quantitative control can be gained. Okay? So you see that your Hamiltonian is going to look like this, right? You have system Hamiltonian, bath Hamiltonian, and there's some coupling, right? And these A's are so-called jump operators, so these guys X on the system. And it's a pretty remarkable and nice derivation from Davies. This is 50 years ago. And he shows that under suitable conditions, then you can approximate this whole sort of complicated joint system by a Lembodian that depends only on the jumps, the system Hamiltonians, the temperature, and a few other bath parameters. Okay. So you can just study this guy. And this guy is, is a continuous time Markov chain, and you can start proving all the things about it. So here's a very concrete example on a qubit. I'm sure you have seen something like this somewhere. So here are jumps. So these jumps are just flipping 1 and 0 to 1. So there are two processes, they sort of the reverse of each other. And then, and they actually have different weights, and these weights are perfectly chosen by nature, actually, such that the Gibbs state is the fixed point. Okay, so the energy gap is 2. So the ratio is exponential minus 2 beta. Okay. So you can convince yourself that if you run this guy in equilibrium, it has to be the Gibbs state, proportional to the Gibbs state. Okay, so this is a rather simple example that anyone could write this down. However, in more generality, if you have a many-body system, it doesn't seem so obvious how this kind of process would look like. Yeah, and indeed, they're actually very, very complicated. It's actually not that easy to just convince to write down something very, very understandable in one slide. But let me first give you sort of an overview of what people have already known. So there's this Davis generator, which is nice in some way. So it has Gibbs state as exact stationary state because it's exactly detail balanced. But then its derivation is actually somewhat unphysical. It sort of only works if the system is very, very small or your system is commuting. Okay. And there's these other Lambadians that is sort of slightly more physical. There's some kind of variation from a Davis generator. We relax some of the derivation. Then you kind of get all sorts of slightly different forms. It's hard to say which one is the best. They also have their own considerations. But I would say one thing in common is that they're all kind of approximate in some way. So all these guys, if you just numerically implement them and see what's the stationary state, it's not going to be the Gibbs state, but something kind of similar to it. And these guys don't have detail balance. Okay, so you see there's kind of a compromise. If you want something exact, it's hard to implement, but the other one, it's so efficiently implementable, but then it's so not exact. Okay. And then so recently, so this line of work that Andras mentioned is that we somehow found something that somehow achieved both, so efficiency and exactness. And there's already a few follow-ups this year that we somehow achieve many of the conditions we liked, and somehow we didn't sacrifice so much anything. Okay, so it's kind of cool that we think that this is maybe a right analog of Glauber dynamics in a quantum world. Okay, so let me quickly mention what these guys are. What these three different kinds are. So here's Davis generator. Okay. So its jump operators its Limbaud operators look like this. Okay, so it's being parameterized by a label A and a label nu. Okay, so what are they? These A are matrix elements that change the energy by nu. Okay, so pictorially, what you do here is you take a flip like a poly X, and then write this in an energy basis, and then sort them by the energy increment. Okay, so nu1 and nu2, there's two x's, and then you would draw this line that sort of change the energy by the same amount. Right, so it's like a band of energy transitions. This orange line, and these are precisely all elements that change energy by nu. And you call this guy your a nu. This is your Limbaud operator. And somehow this is a nice choice that just came out of the derivation. This Davis actually just worked this out and he got this form. Okay. And turns out this guy is so very, very analogous to what people have been doing with Glauber dynamics. So it actually matches what should happen in a classical case. Okay? So in some sense, this is like a quantum version of Glauber dynamics. Okay? So if you find this so very abstract, here's an example for a qubit case. So let's start with the X. This is an off-diagonal matrix, right? And then what's going to happen is that you're going to split it into the part that change energy by +2 and the other part that change energy by -2. And then these will be your two different limb dot operators. So there's these two different processes. You flip the spin to up or go to down. Okay. And then there's this function gamma. I haven't told you what it is. These are the weights you want to associate with these different processes because you want it to be cooling, not heating. And so a very natural choice is this global dynamics looking weight. But what you really want is just that, the heating process has to be suppressed and the cooling process has to be large. And then the ratio, there's like a recipe for it. Yeah, and with this, the whole thing will be detail balanced. And this is all very similar to classical Markov chains that this would imply that Gibbs state is stationary. Okay. So all these things all looks very nice and very reasonable. It reduced to the classical case. However, the problem is that so here you have to first get this guy, and this guy is extremely hard to implement. Right? You have to sort of resolve. You have to cut this matrix A into tiny pieces according to the energy difference exactly. And this can only be done efficiently for a very small system or when the system is commuting. Okay. So there's also other these different versions that's in the literature for a very, very long time. So what's happened here is that you actually try to relax what Davies wrote down. Okay. So what's happening here? So recall that Davies has these limb dot operators, and then you can actually rewrite it in terms of the Fourier transform. Okay, so there's like a time scale t, and you have to take this t to be infinite because you want to know the energy exactly. Okay. And then so in these modern sort of other derivations, all these variants, what happens is that you actually just put like some kind of truncation to the Fourier transform. Okay, so it's kind of physical, right? What's happening here is just that you don't have a perfect resolution of energy; you have a finite resolution. Okay, and this looks pretty arbitrary, but actually this can be derived physically. People in the literature, people actually just work out under some open system assumption, you arrive at this particular limb dot operators. So this can be actually derived physically. And so what's kind of curious is that later on, when we saw this problem, we actually also found efficient quantum algorithm and tools to analyze these guys. Okay, so all of a sudden, this particular object it's being backed by physical derivation, and also is equipped with efficient algorithms. So this is at least give us some basis of doing more theoretical results. And this is not to say all the other ones are invalid. Other ones you can play with. You can still play with them. It's just that you might have to redo some of the tools. You have to remake some of the analytic tools, and it's not always easy to do that. And also, we are not the only. We're really not the first Lindaudian simulation algorithms. There are already a lot of existing work, but somehow, so the one we work out in this paper in 2023 is the one that's tailored to these kind of particular kind of limb dot operators. Okay. Okay. But here, I'm still kind of annoyed because these energy uncertainty is still very, very annoying. It sort of breaks detail balance, and then it forces you to consider approximate Gibbs state, but not exact Gibbs state. Okay. So that seems very annoying. And then, so there's this third one that after all these developments, that we sort of just accidentally found this exact and efficient version that sort of achieved the good parts of both the Davies and this approximate one. Okay, so it's both efficient and exact. Okay, so without showing you what it actually is, it has this nice property. We construct an Lindaudian with the following properties. that arguably matches the global dynamics. Right? So it's detail balanced exactly, but at the same time efficiently simulable, and also the Hamiltonian simulation time is only beta. Okay. And then, if the Hamiltonian and jumps are local, say like a 2D lattice, then so does the Lindbladian. So the Lindbladian is going to be like a local dissipator. Okay. You can draw these light cones around each site, and the radius is going to be roughly beta. And at the same time, this thing we write down is heavily inspired by physics, by the ones I just mentioned. And in fact, it can reduce to Davies for commuting Hamiltonians, and reduce this to classical Glaubers for classical Hamiltonians. So in some sense, it's really like a generalization of these other sort of physically originated Lindbladians. Okay. Okay, so let me just highlight some of the, we think there's some nice other observation and some nice finding. So one thing we sound very, very surprised when we arrive at this exactly detail balanced Lindbladian is that how come you can have quantum detail balance exactly? Right, there seems to be this kind of issue with metrology and exactness, right? Somehow, how do you get to not measure the energy but get exact detail balance? Okay. So here I draw a little picture of a 2D plot. I'm going to try to illustrate the quantum detail balance. I don't know if this makes sense, but roughly quantum detail balance is some kind of pairwise condition between these 2D points. So each point has as Barth and Ketz is labeled by two energies. And then quantum detail balance wants these different state, so these transitions, one way and the other to be related by this Boltzmann factor. So it is a generalization of classical detail balance. But a problem in the quantum case is that you don't actually get to know the energy eigenstates, right? It's not that you can write them down in your notebook. They're so implicit, and then in order to know their energy, you have to measure them, right? So these quantum eigenstates are very highly not accessible for quantum computers. So how do you get to implement this detail balance? And the thing we found conceptually is that detail balance is not about metrology. You never get to know the energy so well, but rather you can. But what you want to do is to have a smooth reweighting of these different strengths. And what we do know is that quantum algorithms are very good at implementing smooth functions. And in this case, these exponential minus beta energy is precisely a smooth function, and the smoothness is beta. Okay. And you don't actually get to know the energy to a very high precision. And second, what's nice about detail balance is that it is a very local quantity. Quite often people talk about phase estimation, but that usually involves a full Hamiltonian simulation. But here, what's remarkable is that if you want a process to be detail balanced, it really suffices to look at a local patch. And we expect this to bring about a lot of improvement and sort of efficiency in the quantum implementation. Okay. So now that I've told you these three sort of maps from physics, might just what do they mean? What can I do? And I would like to say that there's sort of hints that we should actually think about quantum simulation perhaps in a dynamic way, or I guess to view this static problem in a dynamic way. Okay. So quite often you see people discussing Gibbs states. People try to spend their life trying to prove properties of Gibbs states and ground states. But then you sometimes bump into problem about complexity. But still people have been spending some time to get all these nice properties, phase transitions, computational complexity, mutual information, all these properties. But now, if you look at this problem from dynamics point of view, just ask what they actually came from, there's lots of very, very natural problems that now can be doable. Okay. So a very recent example is that is that the complexity of quantum Gibbs states, the gate complexity for preparing a quantum Gibbs state on a quantum computer, was not, and for very high temperature, was only recently proven using our map as part of the proof. Okay, so this is, for example, this is an example of a mixing time analysis. It was done very recently. But then, with this embodiment, you can also ask a lot of other problems that it's not very obvious how you would ask, just looking at the Gibbs state. So for example, the divergence of mixing time, if you start cooling down your sample and you see a divergence in mixing time, this is a dynamical phase transition. And it's not really obvious how you would see this in, if someone only gives you the Gibbs state, right? And if there is indeed a dynamical phase transition, maybe the Gibbs state is not even meaningful. Okay. And so, sort of like a problem, an idea that comes along hand to hand with dynamical phase transition is self-correcting memories. This is a hot topic for some people. And here, whenever something has a diverging mixing time, very likely it could be a memory, right, or a spin glass. Yeah. So here I would like to advocate that if you're looking for new problems, then. And so these newly defined embodiments could be a nice playground to revisit a lot of static problems that people have been thinking about. Okay, and it's not really clear whether dynamics should always be reflected in the statics, and perhaps dynamics itself it's a more fundamental object. Okay. And I have been spending time telling you about all these embodiments, and maybe you're still not convinced why they're useful. And here, hopefully, are some arguments why they're cool. And in the second part of the talk, I'll mention some recent developments and try to give arguments for quantum advantage, in particular using these line of reasoning. Okay, and this is based on these two work. One is very recent. Okay, and I think Robert is also here. We can chat with him. Okay, and I'll actually be somewhat brief about these because they also have lots of technical build up that I don't have time to do. But here's a summary. Okay. So once we so a year ago when we start to build all this machinery, kind of ask what can we use this for. And then it turns out this is actually help us develop these proof. So the first line is this local minimum paper, perhaps you already have seen. So the result there in summary is that low temperature cooling, and for 2D non-commuting Hamiltonians. So this problem itself is actually just as hard as universal quantum computation. Okay, so therefore, if as long as classical computer is weaker than all quantum computers, then there should be a quantum advantage implicitly in this problem. Okay, it doesn't tell us how this speed up come from, so I would say it's implicit. However, in the first line, we actually require the temperature to be extremely low. It has to be inverse polynomially low, so that's physical in some sense. So then there's like a follow-up. There's a different paper that came out later using very different ideas. Sort of based on random circuit sampling, and there the argument is that constant temperature Gibbs sampling is actually you can actually encode a random circuit sampling task. Okay, so this gives an argument that even at constant temperature Gibbs state could be extremely hard for classical computer. Of course, this sort of remains of if you have a constant temperature and then 2D non-commuting, what is the hardness here? How hard this guy could be. So I'll very quickly cover these two results. Very quickly. So in the local minimum paper, what we show is that there's a mapping that takes any circuit you would like to implement and will spit out a 2D Hamiltonian, depending on the circuit, such that the ground state encodes your computation. And then if you just put this guy in the refrigerator in a very low temperature and then you wait for polynomial time, it would give you the ground state. Okay. So here, I didn't specify everything, but here the particular cooling process we use is a variant of Davies. Okay, but we suspect other ones will also work, but this is the one somehow this is the one that works out nice, but it still takes 90 pages. So. And for those of you who have actually seen the paper, we actually featured a different algorithm. It's called quantum thermal gradient descent algorithm. I didn't try to discuss it here. But this is an algorithm that sort of used some mid-circuit measurements to try to improve the cooling process. Okay. Okay, so this is only part of the conceptual claim we're making in this paper. So at the same time, what this paper wants to say is that we should actually think about an alternative problem to ground state problems. The people have been loving ground state for a long time, but also this actually give a headache for theorists because this could be really hard, so QMA hard. Okay? So if you really want like a nicely defined problem that perhaps could better isolate quantum advantage, and here's the problem we propose. So this problem is called a local minimum, the problem of finding a local minimum. So this equation I wrote down there, it really just means that when you evolve under the cooling process, the energy doesn't increase. So in some sense, pictorially, you want to find these values, in your potential. In some sense, very closely, very similar to what, try to optimize, if you run like a gradient descent, you're supposed to get to one of these points. Okay? And here, so the gist is that even for this problem, right, your Hamiltonian could have lots of local minimums, and even if the task is just to find any of them, this is still a very interesting task. Okay? And this task, it's easier than ground state because it's, just by definition, you can always found it by cooling it. Right? If you run the algorithm for a long time, you always get stuck in one of these guys. Okay? But what's interesting here is that, when we carefully tune these Feynman-Kitov Hamiltonians, actually you can make the landscape very nice that you only have a unique local minimum. So therefore, the most naive cooling algorithm will be able to just find the unique local minimum because the potential just looks like is like a ball. Okay. So therefore, even for this reduced problem, this local minimum problem, that's a weaker problem than ground state, it could still be classically hard in the sense of BQP. BQP, yeah, it's BPQ. And for the experts who might have heard other BQP hard results, the way to in some sense the way to view these results is just to say that different computational models are equivalent, up to polynomial reductions. And here I just list some of the ones I can find. There's this Hamiltonian simulation. Actually, I think it actually goes back to Richard Feynman. There's adiabatic computation. There's dissipative computation, and for today, there's the cooling. And then you can ask, what are the differences? It's really a matter of taste because these just intend to capture, different models of computation, right? So in some sense, the message of these cooling, this universal computation by cooling, is to say that a very low temperature bath is extremely powerful. Right? That's what we try to say. And in some sense, it's slightly more robust than previous have considered. And in the sense that we only choose a Hamiltonian, and the rest is given by nature. It's just the thermodynamics that just seems very robust and always works. You just have to crank down the temperature. Okay. But of course, this doesn't really tell you about anything you would normally see in a normal physical system. This is always like a computer science style result. Okay, so that's the first result, and I would like to use the remaining time to discuss this constant temperature result. So this is a little newer, so let me just say that. So if you have so here's the result. So for any constant inverse temperature beta, so constant temperature, we construct a family of n-qubit commuting constant local Hamiltonians such that the Gibbs state is fast thermalizing, but at the same time classically intractable. Okay, so when we say fast thermalizing, it means that the Davis generator mixes very quickly to the Gibbs state. And and if you want to simulate this on a quantum computer, you can do that, and with sort of a low cost, the polynomial cost. But at the same time, because this guy encodes some random circuit sampling experiments, the Gibbs state itself actually is very, very quantum, and supposedly shouldn't be easy for classical computer, assuming some complexity theory assumptions. Okay. So here we crucially leverage the hardness of these so-called IQP circuits. I'm not an expert of these, but this just happens to be one we used. Okay. And then I think there's a very, very recent paper that came out a few days, and in this paper they sort of improved originally our result was log n local, but they still improved it to order 1. Okay, so I just put it here. So what's the idea? The idea is actually quite simple. So let's just start with a Hamiltonian with a bunch of independent z's, and the ground state is going to be 0. Right, and then if you just conjugate this Hamiltonian by a low-depth circuit, well, the whole thing is just going to rotate, right? The ground state is just going to be, C acting on zeros, and the Gibbs state is also just going to be like, the Gibbs state of the non-interacting z's, and you conjugate it, right? But then, so the interesting thing is that you sort of want a circuit with the following properties. You want the circuit to encode an IQP circuit with very, very low overhead. And this is so important to get the locality to be order 1. But at the same time, you want this guy to be fault tolerant to random bit flip errors, so that this guy, it can protect the thermal fluctuations from Gibbs state. Okay, in some sense, all these ideas are not entirely new, but then when you put them together in the right place, it sort of gives you some interesting result. But let me say that these results, there's still some caveats. So in particular, this is not geometrically local. This still requires like a computer science connectivity. And also, the degree is actually logarithmic. So if you look at a particular qubit, it's interacting with many, logarithmically many sites. Okay? And also, we haven't really found a way to very effectively deal with measurement errors. Yeah, so that's summarized. So that's all the things I want to talk about today. To very quickly summarize, so today I talked about Gibbs sampling and the hope for quantum advantage. So sort of want to give a proposal that cooling could be a place where you can have interesting new quantum applications. And I would say there are lots of next things to do, and including interesting new numerics. I think there's very, very few numerics that's been done on this direction. I think there are also lots of opportunities for interesting cooling experiments. I think there's a lot, and including one I think done by Google, I think a year ago. And also, since this is a QSIM conference, I think actually people will talk about some Limbaugh simulation algorithms. So I think there's still a lot more room to do. I think it's really relatively young field than Hamiltonian simulation. So please pick your favorite Hamiltonian simulation problem and then try to make it a Limbaughian simulation problem. I think there will be a lot more to do there. And as Andras said, there's this question of mixing time. I would say really now none of the experts know how to do quantum mixing time. So if you're the first one to do it, I think it will open up lots of new proofs. And classically, Gibbs sampling has been very useful for many other problems. But quantumly, I think we haven't really found like a one that really is very, very punchy. I think there's this STB solver, but so haven't found like end-to-end use. So I would say, since there are so many new things to do here, welcome to join us and expand the program. So and thanks. I'll take any questions.
Maybe we can do a couple of quick questions.
Yeah, thanks for the really nice talk. Maybe you already comment on this, like how fine-tuned are those dynamics? Like if they're kind of, but you also mentioned there aren't that many numerics. I'm just wondering if you are going to implement them as like a simulator, and if one want to make a comparison with like their stability compared with Hamiltonian simulation, like do you have a sense of like if their terms like are they really fine-tuned or if they're robust to like?
Yeah, so their construction looks very fine-tuned, but they sort of roughly still looks like the original one. And then I think there should be numerics soon. I forgot if I actually see one, but I suspect there will be numerics somewhat soon that compares them. Yeah, and I think, but right now I don't know. Yeah, I guess they will all look basically do the same. And for your question, if someone really just want to run this on their device, they should just pick the one that's best for their hardware, because I think hardware seems to be the hardest part. I think here, all this development, and if you take a step back, it's really for theorists to write down something concrete. Does that answer your question?
Yeah. Maybe let me turn the question around. Like, is there a way to design Lindbladian dynamics that would also be robust, like more robust in any sense compared with their Hamiltonian counterpart, or like that's like a separate?
It could be, but I haven't seen any theory developed for that. Yeah, okay. But I think that would be interesting.
One of the advantages of this exact and efficient Lindbladian is that it uses fewer Krauss operators, right? Or uses fewer of these jump operators than the Davies generator. There's some freedom in the definition of these jump operators, so you can kind of mix them with the coherent, the Hamiltonian part. Is it known that the Davies operator can't be implemented, necessarily can't be implemented without using a lot of jump operators?
I'm not sure if there's like explicit lower bounds, but I would say it's very convincing because just from energy time uncertainty. And then you say, in terms of the advantage of these algorithms, I think if you compare with sort of more heuristic derivations, I mean, the advantage is really theoretical. This heuristic one might just works. Who knows? But here, at least if you have detailed balance, the consequences, you can just look at how detailed balance is being used in classical MCMC, or it's used everywhere. And whenever you want to prove a Markov chain mix, first you have to, it better be detailed balance. Then you can study spectral gap. Then everything starts, this machinery start working. So I would say it's really sort of part of this theory. I also just somehow give some conceptually nicer way that it's also, if you have detailed balance, it's compatible with quantum walks. Right? Markov chains, can quantize Markov chains, and you can also do it here. So detailed balance is just somehow very nice. Yeah. But again, like experimentally, you should just do the ones that your hardware is most friendly with.
Maybe you can do the final question right behind.
Thanks for the nice talk. Quick question. Your Lindbladian really not local, it's quasi-local, right? It still has this exponential tails.
That's right.
My question is there a just precise result showing what happens with the error if you truncate it?
Sorry, what's the last part?
What will be the error if we truncate? Is there a just exact theoretical result showing what happens with the error if we truncate it?
We don't quite know, but you can control everything in epsilon, in trace distance. So at least the way we use this, if you're a theorist, the way you use this result is you just look at the ideal one, and you prove everything you want to prove, and in the end you say, okay, if you want to implement this for this long time until the mixing time, here's your budget. So you kind of want to just isolate the analysis and implementation. And if you ask so physically, if you actually truncate it, and then the error actually, if you allow for if you just have very big errors, what happens? I don't know. Like if you truncate them sort of not, if you have a large truncation error, I don't know what will happen.
Okay, but believe if truncation will not change keep state too much, right? It's
well, it would change in trace. It will certainly change in trace distance, but I don't know physically what that would do. I can always do triangle inequality. I know it will give some guarantees, but likely that's going to be very loose.
Thanks.
All right, let's thank Anthony again.